You got it. Okay, so perfect, Nick. That's exactly what we wanted. Okay, so I am giving an update on the surface water monitoring network. So if we go to the next slide, I would like to show you kind of a map of a general overview. So currently we have 17 sites on 12 streams, and we sample for plant available and total forms of nitrogen and phosphorus. And as of 2023, we also started to include chloride, and we sample at each site once a month, April through October. Our sites on the Gallatin at Herringer Bridge to the south, and East Gallatin near Kelly Canyon Road to the east allow us to see ambient stream conditions coming into the valley. Our downstream sites on the East Gallatin and West Gallatin near Manhattan give us insight into potential anthropogenic impacts, as well as maybe naturally occurring sources of nutrients and chlorides in the valley, or chloride in the valley.
Hey,
On our
Drew,
next slide,
why do you sample for plant available and what was the other thing that you said?
plant available and total forms.
Why?
I can touch on
Well,
that, Drew, if you want to keep going. I tackle that in mind, Lily.
sure,
Okay,
let's do
great.
that.
Perfect. Sorry, Drew. I'll
No,
stop.
you're all good. So on our next slide, I want to hit on total nitrogen and N+N concentrations. So to kind of get everybody viewing the same thing here, sites are in relative down gradient order, and they're along the x-axis, and we're going to be reading from left to right. And in the left pane are the East Gallatin Watershed sites, and the West Gallatin are going to be in the right pane. We have concentrations on the y-axis, and they are, again, they're different concentration values based off of their watershed. The big takeaway here, we have 35% or 6 sites are below the numeric standard of 0.3 or 0.3 of a milligram per total nitrogen. We have 3 sites in the East Gallatin watershed, and we have 3 sites in the West Gallatin watershed. See that? Can you click that, Nick? So we have Egal MSU, Bridger, Highlight, the Gallatin, Baker Creek, and then the Lower Gallatin. If we go to the next slide, we have 23% or 4 sites are below the aquatic life standard of 0.1 or 1/10 of a milligram for nitrate, N+N. And that's, again, Bridger Creek, and then 3 sites on the West Gallatin, in the West Gallatin watershed. I now would like to look at the total phosphorus and ortho-P concentrations. So we have 29% or 5 sites that are below the numeric standard of 0.03 or 0.003 of a milligram for total phosphorus. We have 2 sites in the East Gallatin watershed and 3 sites in the West Gallatin watershed. If we can click real quick, Nick. Thank you. So again, Bridger Creek, Thompson Creek, the Upper Gallatin, Baker Creek, and then Camp Creek. And our last one that I want to kind of look at is chloride. So chloride's kind of interesting. This is 2023 was the first year that we started to collect for chloride. If we can do one click real fast. So the elevated concentrations that we're seeing in Matthew Bird and Mandeville Creeks could suggest human impacts for urban runoff, water softeners, septic effluent, and the potential for road salts. And if we click one more, Dry Creek is a pretty cool, pretty interesting one too, because the chloride concentrations that we're seeing there could indicate potentially the chemical weathering of sedimentary rocks, and specifically the Horseshoe Hills area. Most of that is limestone, sandstones, mudstones, and that sort of thing. So really the big takeaway here, we are starting to kind of track changes in nutrients and wastewater solutes to evaluate the effects of human impacts on the landscape. I wanted to keep it nice and tight today, but I do also have temporal graphs as well if anybody's interested after this meeting, if they want to see those.
All right. Awesome, Drew. Thank you.
You bet.
Okay, folks. So Drew has shown us that nutrient levels in Gallatin County or has shown us the nutrient levels that we find in streams and rivers in Gallatin County and how these levels compare to our state numeric water quality standards for nitrogen and phosphorus. Lily, to address your question, we measure plant available forms, which are what we consider to be bioavailable forms of nutrients, because that is the form of nutrients that plants take up as they grow. Plants cannot assimilate organic nutrients. Plants can strictly assimilate or take up inorganic forms of these nutrients. So that is why we measure the inorganic fraction as well as the total fraction or total forms of dissolved nutrients. This informs us about the process of nutrient cycling, which is the transformation process that nutrients undergo between inorganic and organic forms in stream ecosystems. And they're really great metrics for tracking eutrophication, which is the process of nutrient enrichment within our water bodies. So that, I hope that helps answer your question, Lily. We're measuring plant available inorganic forms and total forms. Drew has also shown us some chloride data, which chloride is something that we primarily use as a wastewater tracer. And we can use it in conjunction with nitrate data to assess a lot of properties of stream ecosystems. One of the things that we could just cursory take a glance at is how these things, nitrogen and phosphorus, change in a stream ecosystem relative to one another. So we're treating one as a conservative tracer, something that doesn't react to biota, that's chloride, and we're measuring it at the same time with concentrations of something that is reactive to biological processing. So that gives us great insight into the way streams are connected with groundwater aquifer and ecosystems, the way streams process nutrients, and so forth. So I got to hand it to Drew and his effort to curate this database, because really we're looking at the primary long-term surface water monitoring database in this rapidly growing part of Southwest Montana.
Yeah.
Okay, so turns out that we can use these same parameters, nitrate and chloride, in the groundwater work we do to examine their abundance and spatial distribution and change with time to assess potential impacts to the aquifer as well. So we're using the same parameters in surface water as we do in groundwater to assess human impact. I'm going to turn it over to Xiang Fan, our hydrogeologist, and he's going to talk a little bit more about what we're seeing out there on the landscape with respect to nitrogen and chloride. And there's his amazing baseball card there. Xiang, you ready to rock and roll?
Yep, I'm ready.
All right, let's do it.
Wait, today I'm going to talk about the tracking of nitrate and chloride data in our county for the past 20 years. So what is nitrate? Nitrate is an ion commonly found in water and is monitored in drinking water due to potential health risks at high concentrations. It comes from agriculture activities, animal waste, and septic systems. It indicates agricultural runoff and contamination, helping us to identify human impact on water quality and potential health risks. Chloride is a negative charged ion found in nature, typically as salt, and monitored in drinking water to ensure quality and safety. The salts can be from road salt, agricultural runoff, and industrial wastewater. It indicates contamination from human activities, helping track the movement of contamination, and can reveal impact on aquatic ecosystems and infrastructures. Next slide, please. So where do we collect our data? So basically, we have three sources. The first one is our groundwater monitoring well samplings. You can give a click. This is an overall view map of our all 53 active wells in year 2024. So the green dot is where we are going to sample, or we already sampled this year. So we sampled 7 wells a year, which means we already sampled 14 wells in past May and this June. And our next sampling is this coming July. And you can get hit. And our another source is Big Sky Nutrient Monitoring Project. This is a location of all 8 wells in Big Sky. We sampled 4 times a year from 2018 to 2022. And starting from this year, we're going to sample 3 times a year. Our next sampling is also this coming July. You can give hit. And the last source is our well-educated program. This is a This is a comparison of N+N data before and after 2020. So the average increase of nitrate data for the past decade is 18.1, but we do see some dramatic changes. Is, for example, the well in Cherry River and Mockingbird, over 70%, or we can say it's almost doubled. And for the first, we see a change of 187, is the data almost tripled. You can give hit.
Just to be clear, we're looking at nitrate data right now. So we're looking at the percent change in nitrate concentrations as we observed between recent sampling and sampling from about 18 years ago.
Yep. Thanks, Nick. This is an map view of our data. So you will see this red dot and those yellow dots. So the deeper the dot color, the greater the percentage of the change. And next slide, please. Yeah. This is a comparison of chloride data. This time we see an average increase of 73%, and the more wells the data is doubled, and for the Mockingbird we can see the data is tripled. And if we look at the map view, we can see there's actually no pattern in the distribution of the wells with high percentage of the changes. So we are waiting for our 2024 data so we can have a better interpret what caused those dramatic changes in the past decades. Next slide, please. And here is an application of our well-educated data. For the past 2 slides, we are looking for the data coming from our monitoring wells. Those are the data from the domestic wells. We can see from the 296 wells, 180, or we can say 60.8% of them sits between 0 to 2 milligrams per liters. And 99 wells, or we can say 33% of the wells sits from 2% to 10 milligrams per liters, and only 1 wells it exceeded EPA's 10 milligrams per liters limitation. And there's also 16 wells, or we can say 5.4 wells, as the nitrogen is not detected. And next slide, please. And similarly, this is data from the chloride concentration density distribution. 144 of 185 from the 185 wells, it sits between 0 to 20 milligrams per liters, and 12.8 wells sits between 20 to 250 milligrams per liters, and only 1 well exceeded the 250 EPA secondary maximum contaminate level, and 18 wells we didn't detect any chloride in it. And that's my presentation. Thank you.
Awesome. Thank you, Sean.
Thanks.
I just wanted to cover something real quick, folks. You may be asking, well, why did you look at those concentration ranges that you did? For instance, this 180 observations here between 0 and 2 milligrams per liter. We often think of 2 milligrams per liter as the uppermost extent of what could occur naturally with nitrogen in groundwater. So if we look at this massive bin of 60% of our observations, we could think it's not unreasonable to say here is 60% of the data that have some sort of naturally occurring level of nitrate in their wells. Conversely, we could look at it the other way and say a third of the data is in excess of what could be naturally occurring, or what we could attribute to naturally occurring sources of nitrogen. Said another way, a third of the data is showing anthropogenic influence on nitrate concentrations in groundwater. Similarly, with chloride data, we sort of use this 20 milligrams per liter as the upper bracket for what we could expect naturally, or what we could expect ambient groundwater chloride concentrations to be. Xiong measures a great deal of wells. We've looked at a lot of wells over the past few years. Rare is the case where we see chloride concentrations that exceed 20 milligrams per liter. And that's pretty evident by this graph. So we treat this 20 milligrams per liter as, hey, if you're over that, this is probably showing signs of human influence on the groundwater aquifer.
Thanks, Nick.
Thank you, Sean.
Can I ask a quick question?
Yeah.
Have you plotted the chloride versus the nitrate? And if so, have you seen anything interesting?
What was the first constituent?
Oh, just from that well-educated data, I just wondered if you saw any sort of relationship between the chloride concentrations and the nitrate concentrations.
We've looked at that in Big Sky a little bit, and that's a great question, Tori. Thank you. Like a lot of the times, water resources folks here in Montana and across the nation, they'll use a positive correlation between nitrate and chloride to assess human impacts. Tighter that association, more likely it is that you're having anthropogenic impacts. We did look at that correlation up in Big Sky, and it's very nice and tight in the lower ends of both parameters. But as soon as nitrate gets above 4 to 6 milligrams per liter, the relationship falls apart, which suggests possibly that there are many different sources of nitrogen in that landscape that aren't intimately linked to the chloride signature that we're seeing. Okay, I'm going to keep going here. Thank you. So we saw Xiong talk a little bit about groundwater systems in the Gallatin Valley aquifer system, a little bit in Big Sky, and the things that we monitor for human impact on these resources like nitrate and chloride. What Xiong just showed us in those tables was we can see that groundwater is in fact changing with time, right? It's, and maybe not all places at the same level, but at least in some places it's showing pretty dramatic changes. Generally, it's getting saltier, at least in some locations. And I will say that that's generally what we're trying to prevent, the salinization or increased saltiness of our drinking water aquifer. This, I think, becomes especially relevant as forecasts call for drying climate in the West and their potential impacts on water resources. But we can sort of use these data sources that Xiong and Drew have collected to, I guess we could use the data streams that Xiong has collected to assess this aquifer saltiness and identify hotspots of saltiness. Which I think is really cool and provides us a great understanding into what's going on out there.
Hey,
Xiong
Nick,
also, yeah.
what if I like salty drinking water? Why do I care about salt?
So that's a good question. I mean, in general, the saltier the water, the more impalatable it will be. So I question your judgment on your consumption of salty water, Lily. You know, we have an understanding of like, of the roles of some of these constituents with human health. We know things like nitrate are linked to this condition in babies called methemoglobinemia. So in general, we're trying to watch the abundance of salts in this aquifer. So you could also think of it as they're a pain in the butt to treat. If you want to get that salt out of there, it costs folks quite a bit to employ the technology to reduce the saltiness of their water.
I wondered too about agriculture. I know in other areas of the state that's a major concern. Is that
Yeah,
why?
yeah. I mean, yeah, it's a very valid concern. I mean, I have to acknowledge a lot of the work that has been done in freshwater ecosystems and nutrient enrichment, and agriculture and fertilizer applications are often cited as contributors to nutrient enrichment in stream ecosystems.
And Nick, I was actually asking the reverse, is salty groundwater. So say I'm irrigating my fields with salty groundwater, could that be a concern?
To health, or to human health, or to plants and so forth? Yeah, I mean, there are some general concerns, like the idea of what's appropriate to drink, what's appropriate for human consumption of drinking water is different from that of what could be appropriate to apply on your crops, for example. Generally, it's less stringent, but there are things like sodium and calcium and magnesium ions that have sort of an ideal level for plant growth, and sometimes we see conditions not so favorable out there with in terms of those parameters. So kind of depends on what you're using your water for and its overall condition before you use it.
Great. Thank you, Nick. And thanks for this conversation. I'm going to move us along because I'm kind of looking at the time. Want to make sure all the presenters get a chance and we get a chance to discuss. Thanks.
For sure. Okay. Let's turn it over to Madeline Minutelli, our Montana Conservation Corps intern, and she's going to show us where we've come from in our ability to assess nitrate as a groundwater contaminant in some parts of the Gallatin Valley, and how historical data forms the basis for our understanding of groundwater conditions, right as things were really starting to begin to take off here in the Gallatin Valley in terms of population growth. So we're just going to look at some potential sources of this contaminant and how this investigator in the early 90s determined those potential sources using nitrate isotopes. Madeline.
Awesome. Thank you, Nick. And I'll make sure to keep it brief. Yeah, I'm going to be talking about a study done in the 90s by an author named Eloise Kendi. She published her report here on the right called Magnitude, Extent, and Potential Sources of Nitrate in Groundwater in the Gallatin Local Water Quality District. So in this report, she was documenting nitrate levels in wells across the county, and she was also identifying some potential sources that we were actually just talking about on this call, found in groundwater in Gallatin County. She worked closely with the Local Water Quality District here to complete the report, which was then published by the Department of the Interior and the U.S. Geological Survey in March of 2001. All right, so in her report, from 1992 to 1998, she surveyed over 250 wells around the county. And at 74 of these sites, she measured nitrate levels, where she found an average of 2.46 milligrams per liter of nitrate in the wells, with a maximum of 13.0 milligrams per liter and a minimum of 0.05 milligrams per liter. So kind of looking at what all this means, we can look at the graph on the right here, which has the locations of the wells on the bottom based on their township, range, and sections, and then the nitrate concentrations on the y-axis here. As we see, only one of the wells that Kendi surveyed was above that EPA limit for nitrate levels in drinking water. And then another well was right at that limit, and then one was a little close. But for the most part, all the wells in the county were between that range of like 1 to 5. And so she then touches on what kind of contributes to these nitrates, and yeah, some of these potential sources. So Kendi hinted at 5 different potential contributors, from least impactful to most impactful, they go atmospheric deposition, livestock waste, runoff from areas of timber harvest, and fertilizer and soil organic nitrogen. And then we'll touch on the septic system effluent here at the end. But yeah, she determined that atmospheric deposition was a slight impactor. And then livestock waste and runoff from areas of timber harvest were livestock waste was also a slight impactor, but runoff from areas of timber harvest were moderate impactors, as harvesting the timber kind of speeds up the soil erosion, which kind of creates more nutrient or nitrate rich runoff. And timber harvests are pretty prevalent here in the county. And then she did identify fertilizer and soil organic nitrogen as significant impactors on groundwater, which I know Nick was just talking about a little bit ago. Both natural and anthropogenic, that natural nitrogen and the organic matter of soil, and then also the anthropogenic nitrates from fertilizers being used. But in Kendi's report, she talked about domestic septic system effluent, and she concluded that this was not a major impactor on groundwater quality in Gallatin County. And so if we go to the next slide, we're kind of trying to test the validity of that statement here in the county. In her report, she explicitly stated that on the basis of water quality data from 3 subdivisions, domestic septic system effluent does not appear at present to be a major source of nitrate to groundwater in the Gallatin Local Water Quality District. And she could have come to this report. Most of the septic systems in the 90s when she was writing her report, were either new or in good condition. And over time, as they get older and poorly maintained septic systems, you have a greater chance of the nitrate levels having a greater impact on the groundwater. So looking at long-term projects for the GLWQD, we're looking to revisit some of those wells published in the Kendi report in order to compare the nitrate levels that were published in the 90s versus the ones that we will sample for coming up in the next few years to kind of get that 30-year difference. And then also looking at a septic density map, trying to overlay some of those spots, see the spatial and temporal changes of them. And if we go to the next slide, we can kind of use a map like this as a basis. This map shows the nitrate levels from Kendi's report in 1998. Again, she only sampled 74 of these wells, so there's not a huge distribution of them around the county. But using a map like this could be a really good reference point for kind of analyzing these trends, these 30-year trends, when we collect our own data. So yeah, we'll use this kind of as a basis for comparison. And then I just wanted to also point out that Kendi's data from the 90s shows how our groundwater has historically had small amounts of nitrate levels present in it. So it'll be interesting to see how those trends change over the 30 years. And it's also super important to analyze this historic well data because this data from the 90s is some of the oldest data that we have at the GLWQD to analyze. So it's super important. And yeah, it'll be really interesting to see what kind of trends we see once we get that project going.
Nice, Madeline, thank you.
Mm-hmm.
Questions at this juncture? Okay, moving on. So yeah, Kendi's report, super valuable baseline data for historic groundwater chemical data. We can kind of look at the way that Kendi put together this report and how she attributed potential sources of pollution using nitrogen isotope values. That's what basically led her to her conclusion that septic systems weren't having an impact. She measured isotopes on nitrate, and typically when you have organic sources of waste, such as manure or septic systems, they tend to plot in a predictable place in isotope space. So her points did not plot in that space, ergo her conclusion that septic effluent was not having an impact. However, as Madeline mentioned, we can begin to think about refuting this assertion. If we look at this map of well-educated nitrate data spanning the period of 2015 to 2020, we can see the spatial distribution and magnitude of nitrate in the groundwater. So just pay a little bit of attention to the clustering of these points, because I'm going to flip the map and show you briefly how they may align with old septic systems. So I'm going to toggle back and forth. Here's the map without the old septic systems. We put in a layer to show the density of septic systems reported by Custer in his spatial assessment of septic systems in the county. And honestly, it jumps out at the page at you of where these hotspots of nitrogen pollution are and how they correspond to locations of old septic systems in the county. So it's hard to say from these data alone that septic systems are not having an influence on groundwater. Okay, moving on. We've seen how the role of nutrients come into play in streams and rivers. And we've seen the role of these things in drinking water too. Nutrients fuel not only things like plant biomass, but also bacterial biomass. And nutrient enrichment can be associated with a high abundance of bacterial growth, as well as hazards to human health. So I'm going to turn it over to Paige Tollison, who's going to tell us about two forms of hazards to human health that are associated with increased nutrient abundance in Gallatin County. Pager.
All right, thanks, Nick. Hi, everyone. Today I will be talking about the Recreational Waters Monitoring Network. So, oh, next slide. Yeah, there we go.
Sorry.
That's okay. Okay, so the Water Quality District routinely monitors recreational waters around Bozeman that people and dogs frequently swim in. And we monitor these water bodies for harmful algal blooms and E. coli bacteria because they can negatively impact humans and animals' health. So for recreational waters, anything above the geometric mean of 126 colonies per 100 milliliter samples are above the EPA's recreational water standards. And if E. coli levels are above this standard, it is advised not to swim. Next slide. So in 2023, this graph shows our E. coli results, and the sample locations are located on the x-axis and E. coli counts on the y-axis. Last year, we sampled 3 separate sites for E. coli and only saw E. coli levels reaching above the recreational water standard for one site, which was at Myers Lake. Next slide. Okay, and we also monitor these sites for harmful algal blooms. So what are harmful algal blooms? They are caused by blue-green algae that's native to Montana. And not all blue-green algae produce harmful toxins, but some can produce dangerous cyanotoxins. And some species can produce excessive biomass as well, which is the big blooms that you see. And toxins include microcystins and anatoxins. And we see a range of health effects from both these toxins in humans and animals. Symptoms vary depending on which toxin has been ingested. Microcystin is a liver toxin, and anatoxin A is a neurotoxin, and anatoxin A is known for its very fast death factor. So it's nasty stuff. Next slide. So in 2023, our HABs testing results, out of the 5 sites we monitored, we only had one positive result, and that was at Elk Grove Pond. And next slide. And in 2024, we will be sampling at the following sites for E. coli and HABs, including Glen Lake Rotary Park, locally known as Bozeman Beach, at Bozeman Pond, which is often known as the Mall Pond, at Gallatin Regional Park, and at River Rock Subdivision. And then we'll also be sampling for HABs at Highlight and North Lake Pond at Gallatin County Regional Park. And only HABs there just because that's a dog swimming area. People don't swim in there very often. And yeah, that's all I got. Thanks, everyone.
Nice. Thank you, Paige.
Yep.
Okay. Kind of big picture summary. We saw some of these data from Paige from our recreational water site. The sites that we monitored, there's this one hotspot issue that, frankly, you wouldn't want to swim in anyways if you saw this thing. It's duck fueled, poopy pond scene, so don't go in there. But generally speaking, E. coli, not a tremendous issue out there on the landscape, right? We're seeing most of these observations are below this threshold for full body contact swimming, so that helps them sleep better at night. But we do want to keep an eye on this issue as drought may continue or come into play here, and as groundwater use around these ponds ramps up. A number of these ponds that have the low quantities of E. coli, they're dominated by groundwater inputs, so they tend to remain cold. Cold temperatures aren't the best for bacteria. The bacteria don't do too well in these groundwater fed ponds. But you can imagine if people started sucking up the groundwater near one of these ponds, you may see reduced inputs of groundwater, and this stuff started to take off. So we're keeping an eye on that. Also, when you're out there, these harmful algal blooms, they are a thing. They do exist, and they do happen in Gallatin County. So if you're out there and you got a dog or you're going to go swimming, watch out for toxic algae. Or at least watch out for signs warning you about toxic algae. Okay, I think that the occurrence of harmful algal blooms is generally increasing throughout Montana and across the country as nutrient enrichment increases. We hope that we may hold some predictive power into being able to say, hey, these things might occur in this pond when due to nutrient ratios of nitrogen and phosphorus. So we can track those relative to one another. And it just so happens that these algal blooms tend to kick up when nitrogen availability is reduced. So they are end fixers. They create their own nitrogen. They're net importers of nitrogen into these pond ecosystems. So we see declines in this plant available nitrogen, up sprout the harmful algal blooms that are also nitrogen fixers. And it's kind of a little vicious positive feedback cycle. But yeah, the general occurrence of these things, the frequency and the magnitude of these things, probably increasing on a regional basis. Okay, I know we're short on time, so I'm going to jump right into it, okay? One could reasonably ask us the question, hey, local water quality district, why do you measure the things that you do? And I was thinking about that, and I thought of the Temptation song, the way you do the things you do, and the lyric, you could have been anything that you wanted to be, and I decided to devote my career to freshwater science. So I'm happy as a clam to be in that position. So why do we measure these things? Well, we generally care about the public's understanding of our aquifer resource, our rivers and streams, and the conditions found in the swimming holes. Ultimately, there is inherent value in the long-term ecosystem monitoring that we're doing because the monitoring is generating data sets that will facilitate understanding of the long-term changes to the integrity of these ecosystems that we monitor. In generally, we care about the integrity of aquatic ecosystems. Okay, so we can think about this process of nutrient enrichment, or eutrophication as it is called. And I came up with this simple conceptual diagram to sort of illustrate this concept. We're looking at, here we are, time one down in the left-hand corner. We've got time along the x-axis and eutrophication status along the right axis. Here we are at time one, present day. And I think that if we were to look into the future towards time two and proceed with the status quo, we can anticipate the manifestation of eutrophication occurring more frequently and at a greater magnitude as time progresses, such that in the future, I hope the main stem Gallatin does not look like this picture of the Clark Fork that I snapped in 2016. And I would also say that in between time step one and time step two is this gray box, which I've described as what happens in this time is up to us. That is to say, if we want to prevent or control eutrophication, there are things that we could be doing to accomplish that. Okay, so one of the main things, one of the main ways that eutrophication manifests, or nutrient enrichment manifests, is increasing algal abundance driven by this increased nutrient abundance, right? So we see down the road large blooms of benthic algal biomass. And I just wanted to say, despite recent reporting in the Bozeman Daily Chronicle, toxic algal blooms are likely not occurring in the West Gallatin River below Big Sky, as was reported. Page touched on what is a harmful algal bloom that produce cyanotoxins. That is not the same as what is occurring in the main stem West Gallatin. What we're seeing in the main stem West Gallatin is the seasonal development of what has been cited as the most ubiquitous alga in the Northern Hemisphere, and probably on a global basis, that belongs to the genus Cladophora, a type of green alga that occurs on every continent. I'll say in the right conditions, this stuff grows like a weed. Its doubling time, literature cited doubling time of 10 days. So it can double its biomass on the riverbed in a matter of 10 days when conditions are right. And it just so happens conditions happen to be just about perfect here in the shallow sunlit rivers of Western Montana. So I wanted to explore this idea of nuisance algal blooms and why they're important for our stream ecosystems.
Okay, and Nick, just to time check, it's 2:15.
Okay, I got 5 minutes. I'll jam through this. So specifically, when we're talking about a nuisance algal bloom, we're generally talking about the manifestation of the life history of the alga Cladophora. We call that the phenology. So the springtime, this stuff grows up to some maximal biomass. Conditions that support that biomass tend to deteriorate. The stuff breaks off, and generally biomass declines over the course of the year. This resets every year, right? And when concentrations of this algae on the stream bottom get to be so abundant that they exceed or hit 125 milligrams of chlorophyll A per square meter on the stream bottom, the state of Montana deems that a nuisance algal bloom. It's a nuisance to recreating. It's a nuisance to the beneficial uses or designated uses of this stream. And it's a general pain in the you-know-what. Okay, so what do those algal blooms do that are bad for rivers? And I gotta say, not all algae is bad, folks. I think algae is getting a real bad rap out there. Algae is the fundamental component of the riverine food web. It is the source of carbon that drives the flow of energy through the food web. And ultimately, it is why we have trout in the river. If there was no algae there, there'd be no trout. So not all algae is inherently bad. However, when the stuff grows to nuisance proportions, like we see here, it does have some effects on the river ecosystem. This is data from the 2015 in the Clark Fork. We took oxygen sensors and stuck them in the water column, where we see typical dissolved oxygen that declines during night and rebounds during the daytime due to the process of photosynthesis. We stuck—
Great. And Nick, about one more minute.
Okay, we stuck at the same time sensors down in the river bottom. We can see a fraction of the dissolved oxygen levels in the river bottom. Generally, those types of conditions aren't conducive to riverine food webs, right? We're seeing low dissolved oxygen, but we're seeing organisms that have gills and rely on oxygen to do what they do. So essentially, this process of nutrient enrichment causes algal blooms, which can cause low dissolved oxygen via respiration of all this plant biomass at night when photosynthesis isn't occurring, and also through decomposition. When the stuff dies and sloughs off, it sucks up the oxygen. So when we have these situations or scenarios on the river bottom of abundant algae, we typically see shifts in the riverine food web from complex, diverse, abundant, and nutritious bugs that have gills that rely on oxygen to do what they do, shifting towards more simplified food forms available as forage for fish. So we're going from abundant and nutritious to, hey, algae bloom, low dissolved oxygen, scarce food forms, and ultimately wafer thin. So we're seeing a simplification of the river food web. ultimately, we have to think about controlling the limiting nutrient. And I have not enough time to get into this, but essentially we can look at this point right here where the arrow points onto the West Gallatin. This suggests that this river ecosystem, the primary productivity in it, the creation of new biomass in it, is limited by the supply of nitrogen in this river ecosystem. So that, said another way, this site on the West Gallatin is going to respond most quickly to any inputs of nitrogen, and probably to, if we tried to take nitrogen out of the system, it would hopefully respond just as readily. But we're really concerned about this limiting nutrient because that suggests what we may be able to control on the landscape in terms of nutrient inputs. If we identify a system that is nitrogen limited, then we want to control the availability of nitrogen in that river ecosystem. I'm going to stop right there. Happy to answer any questions. Thanks, everyone.
Thank you.